Okay, so we've defined the derivative of a function at a point, f prime of a. So for a function f of x, assuming this limit exists at x equals a, this gives the instantaneous rate of change at a. It gives the slope of the line tangent to the graph of f of x at x equals a, etc., etc. Okay, so what we're going to do now is define actually a new function. So define a function f prime of x. Now here x is a variable, but the function is just going to be this limit of this difference quotient, f of x plus h minus f of x all over h. And now this is called the derivative function. Okay, now of course, this function has a domain. It has a natural domain. And its natural domain is going to be related to the domain of f. In fact, it's going to be contained in the domain of f. So the domain is going to be the following set. So first of all, we're only going to include x values that are in the domain of f. So it's the set of x values in the domain of f for which this limit f prime of x exists. So this function, well, what are the outputs? Well, the outputs are the derivatives f prime of whatever number I plug in. But I'm only going to get an output if the function is differentiable at that point. And of course, it doesn't make sense to try to see if a function is differentiable at a point if that point is not in the domain of the function. So that's why we're really restricting to just looking at x values in the domain of the function. And from this definition, it's clear that the domain of f prime is going to be a subset of the domain of f. So we're not going to have any new points. But in general, there are going to be points in the domain of f for which f prime of x does not exist. So really, this is going to be in general a strict containment. There are going to be points in the domain of f that are not in the domain of f prime. So let's make some of this terminology a little bit more clear. So f prime of x is defined as a function at x equals a exactly when f of x is differentiable at a. Okay, so we have another way to just say the same thing. A function is differentiable, the derivative exists, f prime of x is defined at x equals a. Again, all of these things mean exactly the same thing. But what we'll say is that f of x is differentiable. And so now notice I'm not saying at any particular point. Differentiable if f prime of x is defined at every point in the domain of f. So this is very similar to our conversation about a continuous function. So a function could be continuous at a point, but we also said a function was just a continuous function if it was continuous over its whole domain. Similarly here, a function is differentiable if its derivative function is defined at every point in the domain of f. Or maybe if we restrict just to some open interval, we say f is differentiable over that open interval if the derivative is defined at every point over that open interval. So again, there's going to be a lot of terminology, and it seems to be that there's a lot of abuse of terminology around derivatives, because you're already saying derivative at a point, differentiable at a point, derivative function defined at a point, but then you also have differentiable over an interval, f prime of x defined over an interval. So it's just a lot kind of muddied up in the waters now. But for now, we're really going to be talking a lot about the derivative at a point. So f of x being differentiable at a point, the derivative existing at a point, the derivative function being defined at a point, etc. So just take some time to think about all these terms and these definitions, relax and understand that they're really saying the same thing. They're just used in slightly different contexts, just to mean different things. Okay, so we want to talk a little bit about what the derivative is telling us. And what does it tell us specifically about the function f of x? And now, we're going to spend a lot of time talking about this question, but we just want to introduce it right now. So here are just a couple things. F prime tells us where f of x is increasing and decreasing. And now why is that? Well, when the derivative function is positive, what that means is that all of those x values correspond to points on the function that have positive slope. In other words, the derivative is increasing. The function is increasing, the derivative is positive. And then also where the derivative is negative, that tells us that the function is decreasing. It also tells us where f of x has horizontal tangents. And what's the significance of a horizontal tangent? Well, we'll see later that horizontal tangents, and now what I mean by that are points on the graph of f of x for which the tangent line is horizontal. And those are actually points where the function is potentially changing from being increasing or decreasing. And this has a lot of physical significance. So for instance, physically, horizontal tangents can signify when a ball reaches its highest point, because the ball in that point is changing from having a positive derivative, so a positive velocity, to a negative velocity. So it tells us about changing directions. Again, it's going back to understanding how functions are changing. Here's an economics example. The horizontal tangents will tell us when a profit function has an optimal profit. So for how many units of something should I sell to maximize the profit? Well, that's going to occur when the function has a horizontal tangent. So it's telling us a lot of information, and horizontal tangents will take center stage when we discuss applications of the derivative. And we're going to discuss a bunch, and as you'll see, these horizontal tangents are extremely important. So this is just something to keep in the back of your mind. We're going to hit on all of this later, but the derivative function is telling us a lot of information about f of x. So I want to go back and talk about the relationship between continuity, so where a function is continuous, and then differentiability. So function being continuous, function being differentiable. And so what we know is that being differentiable is stronger than being continuous. Okay, so in other words, differentiability tells us that a function is smooth at a point, so it's varying smoothly, whereas continuity just says that there's a connection. So you can see that a function can connect, like at a corner, and not be smooth. But it's necessary for a function to be smooth that at least the function be connecting at that point. Okay, so precisely what do I mean? Well, what I mean is if f prime of a exists, okay, and now notice there's lots of different ways to think about this. I'm saying that the derivative function evaluated at a is defined, or this limit exists. It doesn't really matter how you think about it. The tangent line exists, etc. Then, what can I conclude? I can conclude that f of x is continuous. At a. So this is what we call a property being stronger than another property. Differentiability implies continuity. So let's actually see why this is the case. So we can actually prove this statement. Now we're not going to do very many proofs in this class, but we do want to highlight the simple ones, the ones that don't really require a lot of depth to understand. And so the proof here is pretty simple. We're going to assume that this exists. Limit as h approaches 0 of f of a plus h minus f of a all over h exists. So this is what we know. So what we want to show is that the limit as x approaches a of f of x is equal to f of a. Okay, but what is the limit as x approaches a of f of x? Well, what I can do is some magic. So the first thing I'm going to do is I'm going to take f of x, subtract f of a, and then add f of a. Okay? So all I did is subtract f of a and then add f of a. So these are still equal. And now I'm going to do one more thing. So I'm going to add f of a back. But what I'm going to do first is I'm going to divide by x minus a, and then multiply by x minus a. And now notice, because I'm taking the limit as x approaches a, I'm not multiplying and dividing by 0, because I don't care about what happens when x is equal to a. But now, the limit as x approaches a of this difference quotient is exactly the same thing as the limit as h approaches 0 of this difference quotient. The only difference is I just need to let x equal what? Well, I need to let x equal a plus h. And then we see as h goes to 0, x is approaching a, and then you just plug in a plus h, you get exactly this. But this exists as a limit. This is what we're assuming. So we can actually just apply the limit laws. So I can take the limit of this factor times the limit of this factor. So this is f prime of a times, well, the limit as x approaches a of x minus a is 0, so times 0. And then the limit of the constant f of a is just f of a. But this is a number times 0, which is 0, plus f of a. So all in all, we have f of a. So the limit as x approaches a of f of x is just f of a. But that's exactly what we need to show that the function is continuous. So if a function is differentiable at a point, it must be continuous. And while this seems like a really simple fact, it wouldn't be that useful, it is extremely useful when you start talking about the differentiation rules and some of the rules that we want to use to make finding derivative functions easier. So what about the converse? Now converse, I mean the opposite statement. And so we just said and concluded that if a function is differentiable, it has to be continuous. But are all continuous functions differentiable? Now I'll let you think about that for a second. So of course the answer is no, and we've actually already seen an example. Absolute value of x is continuous at 0, but not differentiable. And this is kind of the go-to example. If you're ever asked, give an example of a function that's continuous but not differentiable. Absolute value of x. It's continuous at 0 because the limit from the left is 0, limit from the right is 0. But those two piecewise functions are meeting at a corner. They're not meeting smoothly. That point where they meet is not differentiable. So just a couple of notes, just to kind of generalize this idea. If f of x has a corner, then the derivative function will have a jump discontinuity. Jump discontinuity. this isn't too hard to see because meeting in a corner just means that the two slopes are not lining up. So if I think about the derivative function telling me the slope everywhere, like for absolute value of x, at 0, the slope is -1, but then at 0 it jumps up to 1. So there's a jump discontinuity in the derivative function. Okay, and then also, if f of x has a vertical tangent, or a cusp, then what can we say about the derivative function? Then f prime of x has a vertical asymptote. And why is that? Because remember that a vertical tangent or a cusp had the slope of the function going either to plus or minus infinity in one direction. But that means that the derivative function is getting bigger and bigger and bigger and bigger, or further away from 0, I should say. Whether it's positive or negative doesn't matter. So f prime of x is going to have a vertical asymptote. So these are just some facts to keep in the back of your mind, and they'll come up as we look at the examples. So the very last thing we want to talk about with derivative functions is something that's kind of obvious, but I think it needs to be very explicitly said. And that's the concept of higher derivatives, second derivatives, third derivatives, fourth derivatives. But the idea is really simple. Let's start with the second derivative. So the second derivative this is just the silliest definition to me. The second derivative of a function f of x denoted, so the derivative was f prime of x, so the second derivative will be f double prime of x. And what do you think it is? Well, it's the derivative of the first derivative. Easy as that. So if you find the first derivative function, then you just take the derivative again. Now you may have to exclude some points where the first derivative is defined where the second isn't, but that's fine. But we have a second derivative function. And of course, similar for higher derivatives. And so notationally, for higher derivatives, we have the third derivative, which is the derivative of the second derivative. But at some point, if you take the 10th derivative, you don't want to put 10 primes. So what you sometimes do is write in parentheses the derivative that you want. So this is like the third derivative. So that you take the derivative, and then the derivative, and then the derivative again. The fourth derivative, you take the derivative 4 times, 5 times, etc. 5. And then, so sometimes you see something kind of weird. If you ever see f and then 0 of x, so what is the 0th derivative of x? Well, that doesn't really seem to make sense. But what you mean is you just mean the function itself. And so you can sort of think about this chain of derivatives. The 0th derivative is just f, And then the first derivative is the derivative, second derivative, third, fourth, etc. And so, it kind of brings up the question, what's the point of higher derivatives? Okay, so the first derivative tells us the slope of the function, the instantaneous rate of change, the slope of the tangent line. And that's just telling us how the function is changing. But that's kind of a first order description of how the function is changing. What we'll see later, so we'll talk a lot more about the second derivative later on in the course. The second derivative is going to tell us how the first derivative is changing. Now in applications, this is really important. Think back to velocity. So the velocity tells how a position function is changing. But what is the derivative of a velocity function? Well, it should be telling us how the velocity is changing. That's called acceleration. So acceleration is the second derivative of position. And it tells us how the velocity is changing. So again, we'll get into these ideas more later, but we do just want to explicitly say what the second derivative is. So if I want to find a second derivative, I just have to take the derivative, find the first derivative, and then take that function, take the derivative again to get the second derivative. Okay, so we have a function, x squared plus 2x plus 1, and we want to find the derivative of the function, meaning we want to find the derivative function, f prime of x. Then we want to determine the x values that we lose by taking the derivative. So in other words, x values that are in the domain of f that are no longer in the domain of f prime. So in other words, points where the derivative is not defined, points where the function is not differentiable, all the different ways we have to think about that concept. So let's just start. What's the definition of the derivative function? Well, I take the limit as h goes to 0 of what? So I'm just going to write this out. X plus h squared plus 2 times x plus h plus 1. So I'm going to kind of put this in brackets. And then minus x squared plus 2x plus 1. All over h. And then, of course, just notice that this is f of x plus h. And then we're subtracting f of x. All right. Now we're just taking a limit. And now you're really seeing why we did all that work taking limits to get to this point. We weren't just taking limits for fun, we were really practicing taking derivatives because this derivative function is going to tell us so much about the original function. This is an extremely useful computation to do. It's not for nothing. So what do we need to do? If we just try to plug in 0, we're going to get an indeterminate form. But the numerator here is just kind of begging us to expand out and see if anything cancels. And what happens is that a lot of things are going to cancel. So we're taking the limit as h goes to 0 of what? We have x squared plus 2xh plus h squared. I got that just from expanding x plus h squared, plus 2x plus 2h plus 1 minus x squared. So here I'm having to distribute the minus because I'm subtracting that whole quantity, minus 2x minus 1 all over h. And let's see how many things cancel. Well, x squared minus x squared, 2x minus 2x, and 1 minus 1. So we're left with the limit is h goes to 0 of 2xh plus h squared plus 2h. All over h. And now look, we're taking the limit as h goes to 0. So we can actually cancel one of these h's from the numerator and the h from the denominator, because each term in the numerator has at least one factor of h, and the denominator has a factor of h. So we cancel, and we're almost there. Limit is h goes to 0 of 2x plus h plus 2. And what happens now if we let h go to 0? We're left with 2x plus 2. That is the derivative function. It's a function that if I input numbers in the domain of x, of f of x, it outputs the slope of the function at that point. And we'll see a picture in just a second. But let's make the observation that f of x is defined for all real numbers Similarly, f prime of x is defined for all real numbers. They're both polynomials. So what that means is that there are no points where f is defined and f prime is not defined. So in other words, f of x is a differentiable function. It's differentiable over its entire domain. So now let's look at a graph of these two functions. So here we go. In blue, we have the function f of x. It's just a parabola. And then in red, we have the derivative function. And at first glance, you may think, oh, well, this is just two functions plotted. Seemingly don't have any relationship. But look how amazing the derivative function is. Look carefully. Right here, at -3, the derivative function has a value of -4. What does that mean? That means the slope of the function at that point is -4, the slope of the tangent line. And you see as you move on, the function is leveling off, so the slope is getting less steep. But that's exactly what's happening to the derivative. It's getting closer and closer to 0 while still remaining negative. And look at -1. To the left of -1, we have f prime is less than 0, the derivative. But the function f is decreasing. And then we have the cutoff point right here at -1. And then to the right of -1, we have that the derivative function is positive. Or in other words, f is increasing. And we have this amazing relationship between the function and its derivative. The derivative function is just telling you how the function is changing. At -1, notice the derivative function equals 0. But that tells you that the function has a horizontal tangent. There's a horizontal tangent for my function right here. That means, in this case, that f is changing from being decreasing to increasing. So if you think about the position of a car, it means that I'm no longer backing up, I'm moving forward. It's a turning point. So you see the physical significance of that horizontal tangent. And so hopefully just looking at this graph, you're starting to see how amazing derivative functions are. Okay, so let's jump in and try to find the derivative function here. And we just start with what we know, the definition. The derivative, g prime of t, is equal to, by definition, the limit is h approaches 0 of square root of t plus h plus 1 minus square root of t plus 1 all over h. Okay, so we have practice with limits. We try to plug in 0, we're going to get an indeterminate form. So what do we do? Well, what we want to do, we have some square roots, that's a red flag, multiply by the conjugate. So let's multiply by square root of t plus h plus 1 plus square root of t plus 1. Now we have to do that on the top and bottom. We can't just do it for free. And why do we do that? Because the numerator now becomes a difference of squares. And so in the numerator, we have this squared minus this squared. So t plus h plus 1 minus t plus 1 all over h times square root of t plus h plus 1 minus plus square root of t plus 1. Okay, and what happens? We have t minus t, 1 minus 1. So we're left with a factor of h in the numerator. That's going to cancel the factor of h in the denominator. So we're left with something very manageable. Limit is h goes to 0 of 1 over square root t plus h plus 1 plus square root of t plus 1. And what happens as h goes to 0? Well, this goes to square root of t plus 1, so we have 2 square root of t plus 1's in the denominator. So the derivative function just becomes 1 over 2 times square root of t plus 1. That's the derivative function. Okay, so what about the domain of g? That gets confusing. The domain of the original function was the square root of t plus 1. So as long as I don't have a negative under the square root, I'm okay. So it seems like t needs to be greater than or equal to negative 1. So negative 1 to infinity. But what about the domain of g prime? We still have this factor of square root of t plus 1. So we know that the domain is included in this domain of g, negative 1 to infinity. But what about when t is negative 1? When t is negative 1, square root of t plus 1 is 0. So we're actually going to be dividing by 0 if we try to plug in negative 1. So the domain of g prime is actually minus 1 to infinity, not including minus 1. So what does that tell us? G of t is differentiable everywhere in its domain except at t equals negative 1. So g of t is not differentiable at t equals -1. Let's look at a graph of these two functions and see what's going on. Alrighty, so here's a graph of g of t in blue, square root of t plus 1. And then in red we have the derivative, 1 over 2 times square root of t plus 1. And the key thing to notice here is, okay, well the derivative is always positive, and that means the function is always increasing. Another thing to observe. And you can see that initially the slope of the function is very tall, so the derivative is very high, and then it levels off, so the derivative is decreasing. But notice that the derivative actually has a vertical asymptote. And that's because the function has a cusp-like point. So this point here is like a cusp point because it's kind of dive-bombing in, and the slope of the tangent line is getting closer and closer to infinity. But the derivative function is undefined at t equals -1. But the actual function itself is. It's just equal to 0. So it's a really cool phenomenon here that happens where the function is defined at a point, but the derivative actually is not, because the slope at that point is too steep. All right, we know the drill by now. We want to find the derivative function. So let's take the limit. As h goes to 0, in this case we have r plus h to the 2/3. Okay, and then plus 1, and then minus, so this is h of r plus h, and then this is going to be just r to the 2/3 plus 1, all over what? H. So again, notice that if we try to plug in h equals 0, we're going to have a big problem. And that's we're going to get an indeterminate form. So first of all, notice that this does simplify a little bit. So this is the limit as h goes to 0 of, so all of this is equal to h prime of r, of course. So r plus h to the 2/3 minus r to the 2/3 all over h. So all I did is just, this is plus 1 minus 1, so that canceled. But what do we do here? This is really tricky. Okay, so what I would like to do is I would like to actually do something similar to multiplying by a conjugate. Okay, but this is not square roots, this is actually cube roots. So this is a relatively hard example, I would say, but okay, that's fine. It happens. So what I want to do here is I want to multiply by the following factor. R plus h to the 4/3 plus r plus h to the 2/3 times r to the 2/3, and then plus r to the 4/3. And I'm going to multiply by the same factor in the numerator and the denominator. And if you're wondering what I'm doing, kind of like how when we multiply by a conjugate, I'm forcing a difference of squares. Well, here I want to force a difference of cubes. So I'm really just using the difference of cubes formula. So again, you see how useful some of those algebraic tricks can be in calculus. And so what's the point? Well, if I multiply all this out in the numerator, I'm going to get a difference of cubes. I'm going to get this cubed minus this cubed. And if you don't believe me, just distribute it out. Or you can take my word for it, either way. So this cubed is just r plus h squared. So r plus h squared, and then this cubed is also just r squared. And that's over h times, well, I'm going to do something a little bit lazy, but it's not a bad thing to do. I'm going to call this star right here. So instead of writing all this all over again, I'm just going to call it star, and star goes there. Because what's significant here is what happens in the numerator. So in the numerator, we have r plus h squared minus r squared. So if I simplify that out, or I expand this binomial, I get r squared plus 2rh plus h squared minus r squared all over h times star. Okay, and now notice the r squareds will cancel, and I'm left with 2rh plus h squared, and so actually a factor of h will cancel. And so what am I left with? I'm left with the limit is h goes to 0. All I have on top is 2r plus h over star. But the numerator is h goes to 0, just goes to 2r. And then what about star? What happens to star is h goes to 0. Well, we're going to get r to the 4/3 plus, this is just r to the 2/3 times r to the 2/3, which is r to the 4/3, plus r to the 4/3. So we just have 3 times r to the 4/3, which, of course, we're excluding r from the domain here. R can't be 0. But what this is just 2/3 times 1 over r to the 1/3. And that's the answer. That's the derivative of h, the derivative function. So the domain of h is actually all real numbers. I can plug any number I want into h and get a real number output. But the domain of h prime, I lose a point, kind of like in the last example. I lose 0. So the domain of h prime is negative infinity to 0, not including 0, and then from 0 up to infinity. So basically all real numbers except 0. So what that tells us is that h is not differentiable at r equals 0. And what we'll see is that, again, we have another cusp. Okay, so here in blue, we have the original function h of r. And then in red, we have the derivative function h prime of r. And what we can see is that the slope, as we go from the left, is going to be going down to minus infinity. Notice the function is decreasing, the derivative is negative, and getting steeper and steeper and steeper negative. And then to the right, the function is increasing, so the derivative is positive, But as we approach 0 from the right, we're getting really, really steep from the right, so the derivative is going off to infinity. So we actually have a vertical asymptote, x equals 0, for our derivative function, because we have a cusp point on our function. So take a look at that, see if that makes sense. We'll move on. All right, so we want to find the second derivative function of this function, f of x. Okay, so first things first, how do you find the second derivative? The second derivative is the derivative of the first derivative. Okay, so let's just find the first derivative first. So the first derivative is going to be the limit as h goes to 0 of x plus h cubed minus 3x plus h squared minus 24x plus h minus 7. Okay, so that's f of x plus h minus x cubed minus 3x squared minus 24x plus 7. All over h. And of course, if you try to plug in h equals 0, you're going to get an indeterminate form. Unfortunately, we have to expand and hope a lot of things cancel in the numerator. So let's expand the numerator. And in fact, let's just expand the numerator and then write what the limit equals. So expanding the numerator. So we have x cubed from this term, x cubed. I'm just going to use kind of the binomial theorem. 3x squared h plus 3x h squared plus h cubed. Okay, that's from this first term. And then minus 3x squared minus 6xh minus 3h squared. Okay, so that's coming from this term. So I just multiplied this binomial times itself, multiplied by -3. And then minus 24x minus 24h minus 7, but the minus 7s are going to cancel. You see that right away. Okay, so we just have minus x cubed plus 3x squared plus 24x. Okay, so that's what the numerator is. It's a mess. It's very easy to make mistakes, so it probably is a good idea to write this out big and clear, like I'm doing here. And let's see what cancels. X cubed cancels, minus x cubed. We have minus 3x squared plus 3x squared. Then we have minus 24x plus 24x. So all in all, what does the numerator become? So the derivative is the limit, as h goes to 0, of the numerator, which is 3x squared h plus 3x h squared plus h cubed minus 6xh minus 3h squared minus 24h all over h. Okay, and let's cancel one factor of h. So as we kind of expected, everything was going to have a factor of h. But now if we take h to 0, well, 3x squared, that doesn't have an h, so that's left. This still has a factor of h, so that goes to 0, 3xh. So h goes to 0. Here h goes to 0. Here, this is just minus 6x, so that's left. This 3h has a factor of h, so that goes to 0, as h goes to 0. And then we have minus 24. Okay, so that's the derivative. Easy enough. So then for the second derivative, we just take the derivative of the first derivative. So it's the limit is h goes to 0, but now instead of plugging in f of x plus h, f of x, we're going to plug in f prime of x plus h minus f prime of x. So this is going to be 3 times x plus h squared minus 6 times x plus h minus 24 minus f prime of x, which is 3x squared minus 6x minus 24. And of course, all over h. So you see, the important thing to notice here is that the second derivative is just the derivative of the first derivative. So we're doing the same thing we did to find the derivative, except using f prime instead of f. So now if we simplify this out, again, a lot of things should cancel. We have 3x squared plus 6xh plus 3h squared minus 6x minus 6h minus 24 minus 3x squared distribute plus 6x plus 24 all over h. So let's see what cancels. 3x squared minus 3x squared minus 6x plus 6x minus 24 plus 24. We're left with 6xh plus 3h squared minus 6h. We can cancel one factor of h, and all we're left with is 6x minus 6 plus 3h. But as h goes to 0, 3h goes to 0. So all we're left with is 6x minus 6. And that is the second derivative of that function. Okay, so we want the x values for which this function, which should look familiar, has a horizontal tangent. So in other words, we want to find x values such that f prime of x is equal to 0. So in other words, the slope, the derivative is the slope of the tangent line. The slope of those tangent lines is 0. But remember that we already found f prime of x in the previous example. F prime of x was equal to 3x squared minus 6x minus 24. Okay, we just did that by using the definition of the derivative. So if I want f prime of x to be equal to 0, I'm really looking to solve 3x squared minus 6x minus 24 equals 0. So one thing we can do right off the bat is factor out a 3. And that'll help us try to see if we can factor this, what is a quadratic function. So that's minus 2x if I factor out a 3. And then minus 8 equals 0. Okay, and I see that this actually factors. So this is 3 times x minus 4 times x plus 2. So of course, one of these three things needs to be 0 for the product to be 0, using the 0 product property. And of course, 3 can't be 0. 3 is just 3. So either x is 4 or x is negative 2. So these are the x values for which our function has a horizontal tangent.